Hello, my name is Pedro Brito, and my project is cryptography acceleration using FPGA. And now I'm going to give you a short introduction about my project. This project implements a hardware cryptography acceleration mechanism on an FPGA. The system is interfaced with a Linux operating system, and this will provide many cryptography operations that can be used with software such as OpenSSL. My three goals with this project were to have a correct implementation, because if the system is not giving the correct output, it's worthless. I wanted to have high performance, which means low latency and high throughput, so the system could be used to replace the software implementation in any application. And the system should also be modular and reusable, so it's not tied to one specific application but can be reused with many potential applications. The hardware I'm using is the Z board. The Z board has a chip called the ZYNQ. It's both an ARM processor and an FPGA on the same die, so this means the communication between them can be very fast. Some other features I'm using are the gigabit Ethernet and the video output. The encryption is done by the CPU and the FPGA together. First, the CPU will load the key and the initial counter value on the FPGA, and then enable the production of a pad. This pad, when combined with the plaintext using an XOR operation, will give out the ciphertext, which is your encrypted information. The decryption process is symmetrical. You have to first set up the same key and the same initial counter value on the FPGA, and when enabled, it should generate the same pad that, when combined with the ciphertext, which is encrypted data, will then produce the plain text, which is the data encrypted in the first place. The results were very good using AES with 256-bit keys. The OpenSSL benchmark running on the ZYNQ on both cores could do around 45 megabytes per second. Using the hardware acceleration, I was able to reach 180 megabytes on one core or 260 megabytes on both cores. The potential to reach 350 megabytes per second if the software is further optimized. The latency is very good. It's equal or better to OpenSSL, so it can be used to replace this particular algorithm in any application. Some future improvements that would be interesting would be to allow 192 and 128-bit keys. Those are provided by the AES specification but are not implemented in my system. So this will add some flexibility and would allow more kinds of data to be decrypted, because generally 128-bit keys are preferred where maximum security is not necessary. I would like to replace the ZYNQ, which is the current communication solution between the FPGA and the CPU. I would like to put a custom implementation there that should improve performance a lot. And another improvement I would like to make is to put some diagnostic features on the custom logic I developed. This would allow to retrieve internal system states and statistics about how the system is performing, so that would be also very interesting. So now I'm gonna give a short demo about one of the possible applications of my project. What you see behind me is my laptop. It has a video stored in it. It's playing this video and encrypted it. It's sent to this network cable, the raw video stream that's encrypted. It arrives at the Z board. Now, the Z board has a chip. It's called the ZYNQ. The ZYNQ has both FPGA and CPU on the same die. The FPGA is helping decrypt the video, so the Z board is capable of decrypting and playing it in real time, as you can see behind me on the monitor. It's playing the real time the video. Now, if we were to use only software decryption, it would not be able to play it in real time. As you can see, with software decryption only, the Z board is too slow and can decrypt the stream in real time. We need the FPGA to do that. Now, if we were to play the video stream without decrypting at all, what happens is this. You only get static. So if someone were spying on that network cable, this is all they were going to be able to see.